All right, thanks everyone for attending today's webinar. I am just going to pull up my PowerPoint here in just a minute. I'm waiting on it to load up. While we're waiting on that, for those of you who don't know me, my name is Lori Penizak, and I'm a spectral geologist here at Spectral Evolution. And today we're going to talk about some of the applications that you can use with a field spectrometer for the lithium mineral applications. So at the end of the webinar, you'll see my email will be posted. So if you have any questions, make sure that you email me directly afterwards. All right, so what we are going to cover today will go as follows. So I'll give a quick overview of who we are and what Spectral Evolution does in regards to our products. I'll then go into some of the lithium-bearing mineral applications that you can use this technology for. And then we will actually look at a quick case study and the spectral data from that, ending with an easy ID demo where I'll actually show some of that spectral data in our mineral analysis software. Spectral Evolution is the leading manufacturer of high-quality ultraviolet, visible, and near-infrared spectrometers and spectral radiometers that cover full range from 350 to 2,500 nanometers for a wide variety of applications and industries. So we were established in 2004, and we manufacture all of our products in-house in Massachusetts. I mentioned the various industries that you can use these instruments in. So those include different hyperspectral applications, remote sensing of vegetation, mining and geology, which is what we're talking about today. And we also serve the photonics and calibration transfer industry as well. So if there's any of you here who are interested in any other applications that we're not talking about today, make sure you email me afterwards as well. So since we are covering, mining and geological application today, let's just quickly go over the products that we offer for this market. The Ore Express here on the far left, this is our standard spectral resolution spectrometer that most of you here are familiar with. So you've got a 2.8 nanometer resolution in the UV-Vis, 8 nanometers in SWIR1, and 6 nanometers in SWIR2. Now, spectral resolution really prides itself on innovation, and that's why we also now offer 2 higher spectral resolution instruments, including the Ore Expert, which is here on the far right, which happens to be the field portable spectrometer with the highest spectral resolution in the world, down to a 1.5 nanometer spectral resolution in UV-Vis, 3 nanometers in SWIR1, and 3.8 in SWIR2. So the Ore Expert here actually gives double the spectral resolution that you get if you were using the Ore Express. So, if you're someone who's interested in seeing additional features in your spectral data, make sure you email me at the end of this webinar to get more information on any of these products. So these instruments are truly portable in the sense that, maybe today we're taking data of samples in a lab or in an office setting, and then maybe tomorrow we might want to go out into the field and take measurements on outcrop or in the true exploration environment. So you can put these instruments into a backpack, like as you see pictured here, and take these into the field. Now, a popular option for these instruments is to use them in the core shack as well. So you kind of have to imagine you could put the spectrometer on a cart, and as you go down the core to take measurements, you would just push the cart along. And we've got 2 style contact probes, one with a 10 millimeter field of view window and another with a 3 millimeter window. Now, your application is really going to depend on which one of these probes you use. at the time of measurement. So for example, if there's a specific vein or an area that you're trying to measure, the 3-millimeter mini probe works great for that. But if you're someone trying to get a good average of, say, for example, your white mica alteration, the 10-millimeter probe would be best for that. So both of these probes are designed to fit comfortably in a chip tray, and they have that ergonomic handle with a trigger function. So all of our spectrometers that we offer operate via Bluetooth in the field by a laptop or a rugged tablet as well. All right, so let's get into the actual application here at hand, lithium. So most of you here know exactly why we care about this application due to you being geologists yourself, but there are a handful of people attending today who are not geologists and may not truly understand the importance of this application. So I'm just going to give a quick overview of why this is. Now, lithium is a critical metal because of its vital tendencies for these clean energy technologies. So you kind of have to think about, batteries for electric vehicles, for example. So currently around half of the world's lithium is extracted from pegmatites, with the remaining coming from brines and clay deposits. So understanding the mineralogy of these lithium-bearing mineral deposits is crucial to this application. So this is where using a field portable spectrometer comes in handy. So using one of our OR-X series units, you can identify and track these important mineral assemblages associated with these, lithium contents in these different types of deposits. Like I mentioned previously, the majority of the world's lithium is coming from pegmatites. But you can also find lithium-bearing brines and also lithium-bearing clay deposits as well. So a field portable spectrometer is going to help you identify lithium-bearing ore minerals, distinguish between clays and lithium-bearing clays, and also those micas. So let's take a look at spectral data from these minerals. Now, the most common lithium-bearing ore minerals are spodumene, petalite, lepidolite, amblygonite, and triflite or lithiophyllite. So on the far right here, this is going to be a plot showing the spectral data of these minerals. So the way this works is these minerals are going to have distinct spectral signatures and absorption features based on the molecular bonds of that mineral. So I should note that, so if you look here in this plot, the top right, so this is a spectral signature of petalite, and the blue one below that is a spectral signature of spodumene. So what I want to talk about really quickly is that typically spodumene is going to be mixed with quartz or some kind of smectite. And so spodumene and petalite look very similar. And so for this application in particular, distinguishing between petalite and spodumene, it's going to take more research with ultra high resolution to see if we can distinguish between these two specifically. So however, if you can clearly see though that you can distinguish between, for example, the green here, this is lepidolite, you can distinguish between spodumene and lepidolite, and also petalite and lepidolite, for example. So let's see, we're looking at lithium-bearing clays and micas now. So, this is something talking about whenever you're looking through brines or clay deposits, but you can also, in pegmatites, also have these minerals as well. So the most common lithium-bearing clays and micas are going to be lepidolite, zinwaldite, cookite, hectorite, jaderite, basumalite, and swidefordite. So over here to the far right, you can see an example of those spectral data. One of the important applications, which I'll talk about later with the clays, is going to be looking at this cookite, which is the very top here. This is a lithium bearing chlorite technically, but it is a little bit hard to distinguish from kaolinite, especially when you're looking in clay stones. So we'll take a look at that here in just a little bit. All right, so here is actually a common mineral assemblage that you might see if you're looking at lithium pegmatite in particular. So up top here, we're going to start with muscovite, then on to biotite, cassiterite, lepidolite, fluorite, and plagioclase. To the untrained eye, these might not look much different to you, but all of these minerals are going to have different features in different parts of the spectrum from the 350 to 2500 nanometers that can be distinguished even in spectral data that might be mixed with one or more of these minerals, which you can actually do so in softwares like TSG or EasyID, which I'll show a demo of at the end. So one of the issues that we have in pegmatites in particular, especially if you've got muscovite and lepidolite, is being able to distinguish fine-grained lepidolite and muscovite from each other. So this is extremely challenging if you're using a standard resolution spectrometer, so like the OR Express, for example. But with the ultra-high resolution, like the OR Expert, which has a 1.5 nanometer spectral resolution, it's possible. So here is a screenshot where the blue line that you see is the ultra high resolution lepidolite, and the red line is going to be a standard resolution muscovite. Again, to the untrained eye, these might look very similar to you, but if we zoom in here at the 1400 nanometer region, so right here, we can actually see that the lepidolite has more distinct features than the muscovite does. With the lepidolite actually giving a doublet feature, so right here is a doublet feature at about 1400 nanometers and around 1419 nanometers, along with an additional feature here at 1390, which is not seen in the red standard resolution muscovite. So this is one of those applications where that ultra high spectral resolution in the OR Expert proves to be extremely beneficial, especially for these fine-grained mica and lepidolite discrimination. All right, so let's look at what the lithium-bearing clays and micas. This is what a typical lithium clay deposit assemblage might look like. Now I need to point out here, in these type of assemblages, you are going to encounter some feldspars. Now, feldspar is not SWIR active, so that's why this mineral is not going to be listed in the spectral data here. But you can still pick up, like for example, quartz. There are some applications you can work with quartz on. A lot of people tend to use mid-infrared or long-wave infrared for quartz and also feldspars too. But we're going to focus on the actual clay assemblages that you can see. So in this plot here at the very top, you've got that cookite listed in green, followed by hectorite, calcite, lepidolite, illite, and albite. Now, even though I don't have kaolinite listed in this specific assemblage, a lot of you here who specifically work on lithium clay deposits might have kaolinite in your specific assemblage. So let's talk about that for just a minute. All right, so especially those of you who work with clay stones, again, you'll come into contact with both kaolinite and cookite in your assemblages. So cookite is listed here in the blue, and kaolinite is going to be listed here in the red. But just to kind of explain for those who don't understand the cookite application, cookite is actually the dominant lithium-bearing mineral, and so it's intercalated with authigenic illite and deuterial kaolinite. So that's going to suggest that cookite actually forms during this burial diagenesis from those pre-existing lithium-rich kaolinites in an original clay assemblage. So this is why it's important to not only identify when you have kaolinite in these deposits, but also distinguish it from the cookie, which is possible. So this is another application with ultra high spectral resolution with the OR expert that, this is really beneficial for. So the plot here again, you're showing the cookite in the blue and the kaolinite in the red. So both of these minerals do have distinct spectral shapes, and they have distinct spectral positions due to these molecular bonds that they possess. So let's kind of look at a close-up just so we can see the distinctions a little bit better. So here is the close-up of SWIR 1 and SWIR 2 regions, showing this in much greater detail. So again, if we look at the red kaolinite down here in the 1400 nanometers, you've got very sharp, very distinct kaolinite features. If we were to compare this to standard resolution, you would not see as much detail in both the kaolinite or the cookite. But again, also down here in the 2200 nanometer region, they both have ALOH features, completely different shapes as well, and positions. All right, so let's take a quick look at a case study on a characterization of some of these lithium minerals using a portable spectrometer. So this is listed here. So the author was Cardosa Fernandez. This is from 2020. All right, so the geological area that they were taking measurements of samples from is the Fregenda Almendra area in Spain and Portugal. So on the geologic map here, you can see the samples labeled by the red triangles. These are going to be the petalite-bearing pegmatites. The green squares here, those are going to be the spodumene-bearing pegmatites. Pink circles are going to be the lepidolite-bearing pegmatites. And then finally, the blue stars, these are going to be the lepidolite spodumene pegmatites. So the samples that were taken from those areas and measured in a lab, these were taken with Spectral Evolution's SR6500A instrument, which is shown here on the far left. So this actually has the same spectral resolution as the OR expert does. So that 1.5 nanometers, 3 nanometers, and 3.8 nanometer spectral resolution. So this instrument in particular is actually a lab version of the OR expert, although technically you can take this into a backpack into the field as well. So you'll see an example here of some of the samples that they were bringing back to the lab with the 10 millimeter contact probe, and then also our Darwin acquisition software here as well. So looking at the results here, they were able to distinguish between lepidolite and the other two minerals. However, kind of going back to our, previous earlier talk about the spodumene and the petalite, they look so similar that there's definitely going to be need for further research done on those two in particular to see if there's a way to distinguish between them with ultra high resolution and maybe how that might affect it. But in a case where, you've got lepidolite and spodumene or lepidolite and petalite, you can distinguish between those. So you're essentially in a situation where, these spodumenes are going to be mixed with quartz and a smectite. It's usually montmorillonite, just depends on what kind of water you have going on, that you're truly not seeing a pure spodumene. So there, like I said, there's still some work to do on that application in particular, but we are hoping to, maybe resolve it with more research, maybe with ultra high resolution, and try and investigate that, moving forward. All right, so now we are actually going to move on to a demo of our EasyID mineral identification software, and the data that we're going to use actually comes from the same samples from the Cardosa paper. All right. So before I start going into what the data means and what we're seeing in the data, I just kind of want to quickly do a quick overview of anybody who has never seen EasyID or how this software works. So this top left box here, this is going to be all of the actual data that you take, whether that be in real time or post-processing, which is the way that I'm looking at it now. These data that you have in this box are going to be in order. So if I was, taking it in real time, it would in real time populate the box with your data. To the far right box up here, this is going to be the built-in mineral library that we use. A lot of you are used to using TSG, or maybe you're used to using the USGS Spectral library. Because this data was taken with ultra high resolution, currently there's not, any other ultra high resolution libraries except for the one that we offer. So this is our GeoSpec high resolution library. I actually built this library at the Colorado School of Mines, Mineral Museum, and also Harvard as well. So this is all ultra high resolution data. Now the plot itself right here, again, going back to kind of the plots we were talking about in the webinar, the red line that you see is going to be a built-in library spectrum, and the blue line that you see is going to be your actual target data. So whether that's in real time or again, post-processing. To the far right here is going to be mineral scalars. Those of you who are used to using TSG is going to be very, very familiar with this concept. These scalars here are essentially it's a little tool for geologists. So this kind of lets you know, more in-depth information about the geochemical conditions of your actual sample. So for example, if you've got, high crystalline kaolinite versus a weathered kaolinite, for example. All right, so let's kind of get into the data. So I mentioned that, this is the actual data from that paper. So you kind of have to imagine if you're in a core shack and you've got, boxes and boxes of core at different depths. You kind of have to imagine you are taking data as you're going down the core. And so that's how I'm going to explain essentially what the mineral assemblages are going to be as I go through the data. So this first measurement here that I have, this is at the very beginning of the core. So the blue line here is what we took. So it's actually matching to biotite. So if we kind of go back to talking about our pegmatite mineral assemblages, this is data from a lithium pegmatite. So this is going to be very similar to that example assemblage that I was talking about earlier. So as I'm going down, this next sample here, I'm picking up biotite again. As I keep going down, here's where my plagioclase starts to come in. More plagioclase. And then finally, we're getting into an area where we're starting to see some smectites. In particular case, this is where our montmorillonite is showing up. Here we've got some more albite. So far we've seen an assemblage of lots of biotite. We've seen some montmorillonite, albite. This is where our spodumene comes in. Now, these samples in particular are spodumene bearing, but if you didn't know that, again, you would be in a situation where I either have spodumene or I have petalite. That's what you would be looking at. We happen to know for a fact this is spodumene. Now, the reason why our library is actually picking spodumene is because in our library here, we have library spectrums that have mixtures of spodumene and quartz, spodumene and montmorillonite. So different percentages of these minerals we have spectral readings for. So if you wanted to create your own mineral library and do something similar, you could. So again, we're finally hitting our spodumene section of our samples. As we go down, more spodumene. Now we're picking our albite up again. So we're in a very spodumene-rich section of this core. Picking up more albite, more spodumene. Now we're picking up some more plagioclase. Now here is where that fluorite is coming through. So we talked about, you can find, fluorite in specific types of lithium pegmatites. This is the part of the core where we are seeing fluorite pop through. And then now we're back to getting into a heavy montmorillonite and spodumene part of the core, more spodumene. Picking up more plagioclase, albite. And then again, we're in a heavy montmorillonite spodumene part. So again, you know, lots of these spodumene, you know, you can have mixed with quartz, you can have mixed with smectites. In this particular case, we're seeing in our sample lots of montmorillonite and spodumene. Back to albite. So these are just, you know, examples of, as you go down the core, the types of mineral signatures you're going to pick up. Now, if you notice at the end of this, I'm picking up my calcite, and I've actually got some illite as well. So, you know, you've got different parts of the depth that, you know, of your core that you're measuring. If I had continued on, this might turn into more, you know, a different type of assemblage. So just to kind of bring this all back into perspective, you can use this software here in real time to identify the minerals you have and the mixtures as well. So if I'm looking at as a whole, if this was the beginning and end of my core here, it would let me know I am in a heavy spodumene montmorillonite section as well. So that is the end of the demo. So again, that's the end of the webinar actually. So again, my email is listed here. So if you have any specific questions or comments or ideas, please let me know. If you have any questions on any of the instruments, or if you want to talk further about anything, definitely reach out. So that'll be the end. I hope you all enjoyed this, and take care.